Come on, there you go. There we go. We're running now. It let me turn the light off while the thing's running. That's amazing. Just got an update on my phone, and it's pretty cool stuff. Okay, so what I have here is a red laser and a ball of calcite. Boom. Now, if I did a blue laser, it would glow blue, and a green laser will glow green, and I don't know if I have a blue laser here. I did, but I don't think I do now. All right, anyway, that's a blue laser. I mean, a red laser on calcite. Now, here's one. Little larger stone. This is about 80 millimeters here. And what do you think? Yeah, clear. Nice stone, man. Nice stone. Okay, so red laser. What's gonna happen? The whole thing glows. It's not just passing through. And if my blue laser was in here, you'd see it better. The red bigger than the blue, and so it doesn't pick up as much detail. The smaller the wavelength, the more you see the little tiny planes of cleavage that diamonds have, because diamonds have they're all the same size, right? Carbon atoms are all the same size, and they line up in perfect little rows and columns. And so when you move this around, you might find that there's like some flaws in these larger pieces. Oops. There we go. Okay. So diamond crystals go this way. They're up and down the short way, not the long way. And quartz crystals would go this way, right? The long way. This would be the z-axis, and this would be the xy axis. Well, on a hexagonal symmetry, it's supposed to have the long axis and two even short axes, like this and this and this and this. But this obviously doesn't do that, does it? Obviously doesn't do that. And what it really is going like this, and this is the top right here, right there. And you can see where all the planes of cleavage come together. And you can see them reaching these striations, and they go off at an angle. They're not straight across. They leave at an angle that is the same as this, or the same as this, or one of these anyway. Probably this and this, right? This, all of them line up one way, all of them line up on the other way, and they cross right here. And that's the z-axis. And so when I look down here, let's see if we can show you. It splits into 4 viewpoints because because that's the center point for the diamond right there. And when we cut them, see right now all those planes of cleavage are going up, facing up, so that when the light hits, it would hit here and slide downhill on either side. Okay, what we want to do is cut it on this side, right here, and then all of those crystal faces, all of those, see, they're opening outward down here, remember, and so they're opening outwards, and the light comes down this way into like outstretched hands. And that's why diamonds glow. But if you don't cut them the right way, if you don't know that, they don't glow. They'll glow. They'll glow like my calcite stone glows, because carbon-14 gives off electrons when it's excited by laser light at the same wavelength as the light. Okay, and carbon-14 is inside every diamond. And the diamonds are, when you cut them so that they open outwards the right way, then you have a stone that will glow. And so here's one. See this? These are sold on the internet as amethyst citrines. It's got a yellow inside of there. See that? Isn't that cool, huh? All right, and here's the thing: there's nothing cubic about that at all, man. I mean, hexagonal, nothing hexagonal, not even a little bit. And when you see planes of cleavage, quartz does not have planes of cleavage. It can't have planes of cleavage because it's made out of silicon dioxide, and each silicon atom is surrounded by 4 oxygen atoms that are about 4 times bigger than the silicon atom. They're large and fluffy, kind of, and the silicon is a semi-metal, and it's small and hard, but they lock together in a double covalent bond. And silicon dioxide, quartz, is one of the hardest minerals known to man. Okay, that double covalent bond makes it very, very, very hard. Okay, well, diamonds have a double covalent bond that's shared between all 4 of the electrons in its outer valence orbit. So each electron gets its own valence electron, and that is twice as much squared, right? 2 times 2 squared than silicon dioxide. Okay, so it turns out silicon carbide forms in fault lines with diamonds. Okay, I've got a whole bunch of it from my Safford mine, and I've got some very nice pieces. It's put away right now. I've been really sick for a really long time, trying to get better so I can get out and get this stuff to market. And I will this year. This is the year. And we're going to introduce these new diamonds and my gold platinum alloy. And you know what? Monopoly sucks in all of its guises. Whether it's De Beers or whether it's our benevolent government passing out paper money. Um, None of the above is good for us at all. None of the above. Paper money turns free men and women into slaves because that money doesn't carry the value of our labors. It carries the promise of future labors. You see how that works? It's like an indenture to our benevolent government. And I'm sorry that that's true. Very sorry. I grew up on Army bases. My father was a nuclear physicist for the Army. And I remember what America was supposed to be about. And it's not about a bunch of rules and regulations regarding every aspect of human behavior. It's about freedom. And when you have rules and regulations and monopolies that cover every single thing we need to live, and they all belong to someone else, and none of us will ever be able to work hard enough to buy ourselves out ever again because they don't pay us with paper. Do you know what happens if our benevolent government loses its ability to tax us? Do you know what that paper is? It's toilet paper.